So let's say I have a refrigerator right here, and then basically I have it closed off in a sealed system. There's no heat transfer, there's no mass transfer. Basically, it's just this closed off box, and I've got a refrigerator in here. And then I go ahead and I open the door. What do you think is going to happen to the temperature of the room? Now, at first, you might be like, okay, well, there's heat in here. Actually, I mean, there's cold, there's a low temperature, right? So there's heat is going to be basically escaping into this warmer area. So you might be like, okay, well, the room's going to cool down, right? But then you might be like, okay, well, there's also energy coming into the motor, and so maybe that's heating it up. I don't really know what's going to happen. But a way we can tackle this is to look at it from the conservation of energy standpoint in terms of the system. So remember, the conservation of energy says that the change in energy of any system has to equal the energy we put in minus the energy we take out over some process. So if we let our system just be this basically bounding box, the only energy transfer we have is electric energy coming in. Since there's no out, we know that the change in energy has to increase. And assuming that the refrigerator doesn't store it or anything, this energy is eventually going to end up as heat, which means that the temperature of the room is going to increase. Now, there are lots of forms of energy that we might see that we can look at to see whether it's changing or not. So let's go ahead and look at some of the forms we have. The first one we'll have a lot is kinetic energy. So this is basically the energy from moving. If we look at it from the kinematic equations, just to kind of give you a general intuition of the derivation, we know that the final velocity squared is equal to the initial velocity squared for constant acceleration plus twice the acceleration times the distance it's going. So if we go ahead and we divide, or as we subtract over this I squared and divide by 2, we can get that the acceleration times the change in distance is v final squared minus v initial squared all over 2, right? And if you think back to the definition of work, which is where basically we're getting this energy from, because this kinetic energy has the capacity to do work. That's what our energy means in this system, is it can has a capacity to do work or transfer heat. The definition of work is some force acting through a distance. It's called F dot ds added up across some process from 1 to 2. So basically, if I have a vector, let's say this describes my displacement, some ds, and I've got an f right here. So basically, if the object goes from here to here from this force, then we can go ahead and say that the component of this force acting through this displacement is the work that's done. And so usually it's f ds cosine theta, where theta is the smallest angle between these two. So you'll notice that if theta is, let's say, 0, then this term just becomes 1, and it's just force times distance. If theta is a right angle, then we're going to have our force perpendicular to our displacement, and this term goes to 0, which means we can't have any work done. Now, if we substitute in Newton's second law here, and we assume that our force is kind of pointing in the same direction as our displacement, and other useful things like constant force and all of that, this is basically going to turn into force times delta S, which is our change in position, which is mass times acceleration delta S. If you notice up here, we actually solved for a delta S for a constant acceleration. So if we go ahead and plug in our mass, what we'll get is that, I didn't really leave myself some room here. So here's what we're going to do. We're going to move this over here, and maybe we'll just go like this. We'll put this beneath it. Basically, once we plug in our mass, we're going to be able to solve for the energy that's coming from this kinetic. So delta KE, remember that this is a change, is going to be MA delta S, because we're looking at the integral from 1 to 2. If we wanted just the work in general, we'd have to add like the work initial basically. So I guess I should be more specific and say that this is a change, which of course equals M times V final squared minus V initial squared all over 2. And that right there is the definition of our change in kinetic energy for any general process. And that also means that the kinetic energy at some point is just mv squared over 2. This is our kinetic energy. Another form of energy that a system can have is potential energy. Specifically, there's a lot of kinds of potential energy you can have, but we're usually going to ignore some of the more niche ones and gravitational potential energy in terms of bigger macro scale systems are what we're usually going to be looking at. So we know that gravity, if this is our Earth, it always kind of points toward the center, right? If we're on the surface here, just like this. All right. So if you have some object, and let's say I move it from the ground up to here, right? Well, now it has the capacity to move with the weight force, which would point down in this displacement direction. So we'd have a positive F dot ds, which would give us positive work done, which means that when I move this object up, I gain potential energy when I move it against this force. And so our potential energy change is going to equal our work integral from 1 to 2 of our weight force dotted with a ds. And our weight force is mass times acceleration, and we'll go ahead and assume gravitational acceleration. So this is going to give me mg in the downward direction. So we'll just call this mg, maybe a vector like that. It doesn't matter too much how you define these. Dot ds. And since our ds accumulates from this field because it's a conservative field, then it's going to end up being the same as just mg delta s from a kind of vector calculus standpoint. But from an intuitive standpoint, what you can think of is like, let's say that this red is going from here to here, right? This red object. Well, it can take a straight path, or maybe it could take some other path, and we want to know what the change in energy both these cases will be. So if it moves along this path, we have our displacement parallel to our weight force, and so we're basically just going to get force times delta s. And as it takes this weird path, basically we're going to have the accumulation of, well, when it's going down here, it's getting a little bit closer to the Earth, and the component of that that's getting closer to the Earth combined with our weight force is going to give us a small component of an increase in energy. And that'll be canceled out when we go further away. If we're moving basically perpendicular to these weight forces, then our dot product is going to be 0, and the accumulation as we move along this entire path is the same as if we just moved in. If you want to define it more rigorously, you can talk about how it's a conservative force and things like that. But basically, our change in potential energy is a negative mg delta s. And the reason we have a negative sign here is because this is assuming that our ds and our g point in the same direction because of this dot product that we got out. But you can see basically since our weight force is pointing down and this ds is pointing up, they'd actually point in opposite directions. And what this is saying is that if our ds here, if you're increasing the height, then we're going to get positive change in potential energy because now we have the potential to fall down. And if it's going the other direction, we'll have a negative change in potential energy. It all really depends on how you define this ds. And usually we'll call this ds actually as a dz, where z is our height. And this right here is our change in potential energy. If you just want the potential energy, then it's just going to be mgz. But we really care about changes, again, because of this z, it's kind of ambiguous where you call your 0 point, right? I could call it the center. I could call it maybe like the horizon or kind of the flat surface. I could call it anywhere. The changes will never change. Our delta PE will be the same regardless of where we pick our baseline, but our exact potential energy may change. Now we're looking at the macro scale of thermodynamics. There's one more kind of energy that we can have, and that's internal energy. And this is basically an aggregate of all the microscopic processes that are happening. So if you look at some like little particle, some molecule or something, there's a lot of things it can be doing. It can be rotating, right? Like this, you could have some kind of moment of inertia wouldn't be the right word. You could have some polar things going on. It can be rotating. It can be vibrating because it has some kind of bonds. You can have chemical, nuclear. You can have things from spin. There's all kinds of things that can create small microscale internal energy. But when we're looking at the macro scale, we're just going to combine all of these into one big quantity called U. And the way you can kind of think about U's and intuitively, it's kind of just like how much thermal energy it has. Again, that's not completely accurate because there's more stuff going on here than just thermal energy. But a way you can kind of imagine it is like, all right, if the internal energy is increasing, that's kind of like it's heating up. But again, U is all about all of this aggregate internal energy stuff. And so those are the main ways that we can store energy as a system. And some of these are more useful than others. We talked about the second law, how some energy is more useful than others and how there's a certain direction it can go in. Like, for example, kinetic energy is more useful than internal energy. And a way you can think about this is like, let's say I have a paddle wheel, okay? Now, if I had a blob of stuff and it was all moving, let's give it a different color here. Maybe it's like water. Okay, we have water, a blob of water, and it's all moving in this direction. That's going to cause our paddle wheel to spin, and we can extract some work from that. You see that? Because that's going to push these. However, if it just had internal energy, and we kind of imagine that as like thermal energy or heat or something like that, then it's all going to basically be moving around randomly, which isn't as useful as an ordered form of energy like kinetic energy. I cannot extract this to make my paddle wheel turn. I can't turn this thermal energy into work. So some forms of energy are going to be more useful than others. Specifically, work is usually going to be more useful than heat. And work and heat are both forms of energy transfer. And these are the things that are going to cause our energy of our system to change. Energy transfer. So the first one we have is heat, which we call Q. You can also have specific heat, which is our heat per unit mass. And you can have heat done per unit time, which looks like this. Q dot is heat per unit time, so our total heat is our Q dot times a small change in time across our whole time interval, just like this. And so heat ultimately is about a temperature difference. If you're getting an energy change and it's because of a temperature difference, you're looking at heat. Heat happens when we've got basically a system like this. We've got a T2 out here, we've got a T1, and there's energy coming in. And even though this is one way that heat's transferred and heat is all about a temperature difference, it doesn't have to be that. You can also have something heating up because you're adding energy to it, like we saw with this example with the refrigerator. Let me head all the way back up. All right. So here we're only adding in electrical energy, but that's eventually ending up as heat, and it's heating up our system because it's becoming internal to the system. Let me head back down here. Where were we? The second kind you can have is work. And if you have an energy transfer of a closed system, which means we're not talking about mass, and it's not heat, then it's probably work. And we saw that the definition of work is F dot ds. So basically a force acting through a distance gives us work. Now one way you can rewrite this, and it'll be pretty useful, you can see, is we have force and we have a ds. But a lot of times, because pressure is a property, pressure is usually something we have pretty good access to. And remember that pressure is force over area, which means that we can get force as pressure times area, right? And so if we go ahead and we plug this in right here, we can get the integral from 1 to 2 of pressure times area. You'll need a vector somewhere in there, dotted with ds. And then this area and this length, if we think about an area acting, our force is acting on an area, and this is moving at some length, ds right here. So this is ds, this right here is our area. Then you multiply those and you get a change in volume. So this is the same as P dV. You'll have to be careful with your signs here. So I should say equal in absolute value. So the absolute value of this is equal to the absolute value of this. Because of the dot product, that's going to change our signs up a little bit. But P dV is another thing we can use for work. It depends on if work's being done basically to compress our system, decrease its volume, or increase its volume. If work is done on the system, then we're increasing its energy. If work is done by the system, then it's decreasing energy. Same thing with heat here. Heat added to the system is going to increase its energy. Heat removed from the system is going to decrease its energy. And so now ready to give the conservation of energy written fully out for a closed system. Closed conservation of energy. This is also true for an open system. It just will also have mass transfer. That's not a great way of saying this. If we don't have mass transfer, this is a true statement. Otherwise, we can have changes in energy from mass transfer. So the heat added is one way our energy can change, and the work done on the system, but usually we use a minus sign here and say that this is the work done by the system. It really doesn't matter. It just flips what direction work is going in. So is work a positive or negative quantity, basically, equals the changes in energy of our system. So the change in internal plus the change in kinetic plus the change in potential plus some other small things, but we usually just ignore those and say they're basically equal to 0. Our internal energy is just kind of a quantity. We don't really calculate it, but we can get change in kinetic energy by, again, 1/2 m v final squared minus v initial squared. And our potential energy here, change, is mg delta z. Now, another way we can express this is if we divide everything through by mass. So basically, the heat added per unit mass minus the work added per unit mass is our delta U per unit mass, assuming basically that everything's homogeneous, everything is kind of well mixed. There's no properties that are different from one position on our closed system to another. So delta KE lowercase plus delta PE lowercase. And if we think about units right here, this is mass, this is acceleration, so this right here is force. And we also have length. So we have Newton meters, which is also kilojoules, at least in the SI system. Kilojoules. A Newton meter is 1 joule. The reason I say kilojoules so quickly is because kilojoules is usually what you're actually going to see when you're working through a problem, just because joules is a little bit too small for thermodynamic systems you're going to analyze. A kilojoule is just 1,000 joules. Here, since we divide everything through by mass, move this up so it's a little bit clearer. Since we divided everything through by mass here, we're going to have kilojoules per kilogram as our SI unit, usually. Then lastly, if you have a closed system where you're adding heat at a rate, you can divide everything by your change in time, and like the rate of heat added minus the rate of work done by your system has to equal your change in U over change in time plus delta KE over change in time plus delta PE over change in time. This is very unlikely that you're going to see this too often, but it is something that could happen. Okay, now if we're talking about a closed system, we have the problem of mass transfer, right? Mass with itself carries energy. We've seen the ways it can carry energy. We have our U, internal energy. We have our KE, kinetic energy, and we have our PE, gravitational potential. There's some other stuff we're not going to worry about, but there is one more thing that mass can have, especially when it's flowing into or out of our system, and that is pressure times volume, which is a little bit counterintuitive, so there's a couple examples that I think will help illustrate this. The first way you can think about this is, let's imagine a control volume, right? So I've got some volume here. Okay, and let's say I've got an inlet right here, like a pipe or something. And let's say I have a volume that wants to go in here, okay? This blue right here is a volume, okay? And I know that it's coming in like this. Now I could imagine that basically the water, I drew it blue, so we'll just assume this is water, but it could be any fluid. The water behind this is acting with some force that's pushing it in. Now, in reality, this might not be exactly what's going on, but we can imagine it like this, right? There's something that's causing it to come in, some kind of flow force pushing on this. And now notice what we have. We have a force acting through a distance in order to push this in. But we've seen before that we can rewrite our force times distance as P times V. And since we have the volume, usually the pressure is going to be more well known than the force. So what I'm trying to get at here is that pressure times volume describes the energy that's coming in from basically pushing in this water. Another way you can think about this is, let's say you're a wizard, all right? And you're a wizard. You love casting spells. Alright, we're just gonna like quickly draw. I don't know what a wizard looks like. Okay, and you wanna like spellcast something real quick, okay? That's the wizard. Good enough. Okay. But for some reason you want to obey conservation of energy. In order to spawn in, let's just say you want to spawn in a box, okay? Well, I know that this box has some internal energy. Let's assume it has no kinetic or potential energy real quick, so you're just spawning it into space or something with no like gravitational fields or anything like that. You want to spawn this in, boom, you. Alright, well that makes sense. But if you want to spawn it in basically somewhere where there is a pressure, like let's say you want to spawn it in like just on Earth, right? Before you spawn it in, this whole area right here has some air, right? Air. Okay? And so in order to force this air out of here, this volume of air at some pressure, you need to push it out. And so this whole volume pushed out at this pressure gives you P times V. So in order to evacuate all this air and spawn in your box, which has a volume V and is at some pressure P, which is the same as the atmospheric pressure, everything's under this atmospheric pressure, right? Because the air is pushing down on everything. You have to have both U and PV. Another way you can think about this is that inside the internal energy of this box, it has the capacity to basically do work by drawing all of the air at its pressure into this volume. So no matter which kind of scenario makes more sense, you can think about the mass itself, or you can think about a volume and mass coming in, or you can think about the internal energy of it being able to draw on something and pressure at this volume. U plus BV is a very useful term, and it's part of the energy that mass draws in. And it's useful enough that we define it as its own quantity. It's called enthalpy, and it has the letter H. So U plus PV is enthalpy. You can also have specific enthalpy. That's the lowercase u plus p times specific volume. So we pull a mass out of every term here. Okay? And so the energy of a fluid, which they use the letter theta, which is great. I don't actually particularly like this because theta is kind of used for angles. But theta is u plus ke plus pe plus pv, which is the same as h plus ke plus our pe. Okay? So, when we have an open system and it goes through some process, we can add heat to our system, we can add work to our system, or a system can do work, which will give us a decrease in energy, or our mass. Let me put a summation and I'll explain why there's a summation here real quick. Mass inlet times our theta inlet minus sum of mass outlet theta outlet has to equal delta U plus delta PE plus delta KE. Okay, so let's talk about this term real quick. What this is saying is that if I have some volume right here, here's my volume. Okay, and I have an inlet. Maybe I have two inlets because we're adding up for every inlet, because obviously there can be multiple inlets, and every inlet that's dumping energy into this system is dumping energy into it by mass. So our mass at each inlet times our specific internal energy, so lowercase theta. I guess if this is an uppercase theta, we should probably make this a little bit more clear. So let's write it like this. While I'm writing this up, basically what we're saying is that the mass times how much energy per unit mass that's flowing through here is going to give us all of the, that one should still be lowercase, my bad, is going to give us all of the energy that's coming in through that inlet. And then if we subtract the mass coming from the outlets times the specific internal energy from the outlet, then that's going to be all of the energy coming in by mass. So basically, if we have some mass coming in here, mass, right? And that's also coming out. Mass. Basically, all of our mass transfer times the energy per unit mass is going to give us the energy coming in the form of mass. Then if we subtract, the mass coming out, times the energy per unit mass coming out. That'll give us all of our energy flowing out. So our energy per unit mass here is lowercase h plus lowercase ke plus pe, just like that. Okay? So we have Q minus W plus the sum of, if you really wanted to break this out, you could mass inlet times H inlet plus KE inlet plus, you get the point. We would just break out each of these terms equals all of this, right? All of our thetas we could break out into H plus KE plus PE per unit mass. Now this isn't actually used all that often, and the reason is because analyzing processes that are open and there's mass flowing in and out, and we have changes in internal, kinetic, potential, and we have all of these properties coming in at our inlets and our outlets, and we have heat and work, is a lot. Instead, we're going to make an assumption that happens to be true for a lot of systems, or at least is closely approximated, called steady flow. Basically what steady flow says is it's not changing over time. If we have some control volume, which is an open system, okay, and we've got some mass coming in through an inlet, ba-boom, and we have some mass coming out through an outlet, and we're assuming that it's steadily flowing, then the mass coming in equals the mass coming out because our system isn't changing over time. Basically, this is the assumption of steady flow. Our system has stuff coming in, which is balanced by the amount of mass coming out. Mass in equals mass out, and over time it's not changing, and the system is usually running for a very long time. Another way you can think of this is if I had more mass coming in than I had coming out, that would mean that the mass of the system had to increase. And if it's steadily doing that for a long time, where's it going to store it all, right? So this is how steady flow works. And if you think about this, since we have the same amount of mass in here, and everything coming in has to balance with that coming out, our change in internal energy as we're going through time has to equal 0, which means that Q minus W plus all this stuff has to equal 0. So let's go ahead and write this out real quick. Heat added across some process minus our work done across some process of steady flow plus the sum of all the masses at the inlet, and the mass coming in at the inlet, times our specific enthalpy at the inlet, plus our specific kinetic energy at the inlet, plus our specific potential energy at the inlet. All that minus the sum of, I put a minus sign here, right? Yeah, I did. Okay. The mass at the outlet times the specific enthalpy plus the kinetic energy plus the potential energy. All of that has to equal 0. Okay? Now another thing. Since we're assuming conservation of mass, which is another point, I'll go ahead and write this down real quickly over here to the side. Conservation of mass. The reason that we can assume this is because it's mostly true for things that we're dealing with technically. You know Einstein's equation, E equals mc squared. I think divided by some other stuff if you really want to get into the relativity, but E equals mc squared. Energy and mass are the same thing, and you can technically convert mass into energy, but if you're talking about a real process, the amount of energy that you can extract from mass is really hard to do with a real chemical reaction. And so anything that you're talking about as a real process, I'll just leave this here, is basically going to have conserved mass. It's like I said up here. If you're putting more in than you're taking out, eventually it's going to fill up, right? So we're assuming that basically our M in and our M out have to equal each other. And this means that we can simplify this as Q minus W plus just the mass that's flowing both in and out times, this is going to give us H in minus out plus KE in minus KE out plus PE in minus PE out. But I'm going to simplify this as our delta H plus delta KE plus delta PE has to equal 0. And now I'm actually going to pull out a negative sign right here. And the reason is because these deltas are usually with respect to outlet minus inlet. Because you'll see that our labeling convention is basically to call our outlet state 2 and our inlet state 1. And then this will be 2, 2, 2, and 2, and this will be 1, 1, and 1. And now, if I multiply these through by -1 and I pull out this negative sign so that I haven't changed my equation, what I'm going to have is that delta H is H2 minus H1, delta K is K2 minus K1, and then our delta PE is the same. And lastly, what you'll see we'll do is instead of just having this long thing equals 0, we'll just subtract it off to the other side. Equals M delta H plus delta KE plus delta PE. Ta-da, this is a really useful equation. So for some process of an open system, the heat added minus the work done by the system equals the mass that's flowed across times our change in specific enthalpy, so the specific enthalpy of the output minus the input. And remember that enthalpy is a property. And then we'll also have the change in KE from the outlet minus the inlet, and then our change in PE from the outlet minus the inlet. And even more useful than this one might be the rate form, because we're talking about steady flow, which means usually we're going to see we're going to see things moving across per unit time. We're going to have a rate of heat added. We're going to have a rate of mass flow, because this is happening over a really long time. It doesn't make sense to just say, here's the total heat added, here's the total work done, right? So we go down here, the real big equation for a closed system is Q dot minus W dot has to equal M dot delta H plus delta KE plus delta PE, where I basically just divide everything through by change in time. This is the rate form. This is just the static one process form. And so that right there is the conservation of energy. The two biggest equations that you probably want to pay attention to are this one, and for a closed system, since we were talking about open systems earlier, where was it? I could have sworn I wrote it. Yeah, I wrote it up a little bit further. This one right here. Q minus W equals delta U plus delta KU plus delta PE, and then the other things go to 0. These have units of kilojoules. Specific is kilojoules per kilogram. And if we run back down to the bottom real quick here, for a closed system, for an open system, since everything here is in rate form right now, this would be in kilojoules per second. This right here would again just be in kilojoules. All of our terms would be in kilojoules. All of these in here are specific, so they'd be in kilojoules per kilogram if we're talking about SI. I keep saying kilojoules because at this point it's really gotten drilled into my head from doing so many practice problems. You could also use joules per second or even megajoules. It's all just changing by a factor of 1,000 based on the SI system. And technically, if you really wanted to, you could even do these in terms of specifics. So you could have a Q minus W equals, there's going to be no mass term, right? Because we're just dividing everything by mass. Delta H plus delta KE plus delta PE if you wanted to. But again, the big equations I would pay attention to are this one right here and this one right up here. And to be really clear, since there are a lot of deltas between these two equations, this is the change in internal energy or the change in kinetic or the change in potential between our two states of our process, right? So the final internal energy minus the initial internal energy. This one down here, because remember we pulled out the negative sign when we were talking about this. This delta H or delta KE or delta PE means the change from our 2, which is our outlet state, to our 1, which is our inlet state, of these properties of specific enthalpy or specific specific kinetic energy or specific potential energy. And so that right there is the main idea of conservation of energy, which is the first law of, wow, there's quite a lot here, the first law of thermodynamics.